Flat Earth Experiments. Determining the shape of the Earth using tools, observations, and measurements you make yourself, all in your own backyard. Part 5. Shape, Features, and Orientation of the Sun. This video will detail the last of 4 sun observations. Again, we're going to caution that you not look at the sun directly, but instead use proper protection so you don't hurt your eyes or your equipment. Please take this advice seriously. Just Google observing the sun for further guidance. You might only be able to truly appreciate this experiment if there are large sunspots currently visible on the sun. But the entire video might be worthwhile since we'll also discuss theoretical models and how they might relate to what we actually observe in the real world. We'll also point you in the direction of some sunspot footage taken by other YouTube users, so you can use the information in this video to help analyze it. In addition, many of these concepts will also apply to the moon. Here's a quick overview. After discussing safe ways to observe the sun, we'll build a solar clinometer and make a series of sun observations if there are sunspots visible from your location using your equipment. Then we'll look at some models for the shape of the sun. If you were able to see sunspots, we'll analyze how features on the surface of the sun could move in one day's worth of sunshine. The flat Earth has the sun small and close, so the features should sweep to the right, while the heliocentric sun's sunspots should appear to rotate as the orientation of the observer changes, depending on latitude. Supplies. In previous videos, we've recommended that you get a piece of number 14 welder's glass, but we've since learned that you can get some inexpensive solar film designed for telescopes and binoculars, and is optically superior. The number 14 welder's glass is still a good option if you plan on looking straight at the sun with your eyes, while the solar filter film is better if you want to use a camera or binoculars. A digital SLR with a good zoom is essential, and a tripod to keep your camera steady will also help. You'll need a compass bearings diagram that you can print from the internet. And lastly, if you'd like to make a simple solar clinometer, you'll need a pencil, protractor, thread or dental floss, and a weight, like a clothespin or binder clip, plus some cardboard and tape. Here's the plan of attack. First, we'll discuss various options for safely viewing or photographing the sun. Next, we'll describe how to make a simple solar clinometer, which will simply give you another piece of data to accompany your actual sun observations. Then, if there are sunspots visible from your location with your gear, we'll conduct multiple observations throughout the day. Then we'll discuss how to analyze the shape of distant round objects and the apparent movement of sunspots, and how they might relate to the flat Earth versus the globe Earth model. Step 1. Safely observing or photographing the sun. We've repeated this warning before, but this particular set of observations we're going to be intently studying the sun. Thus, we need to be extra careful that we don't hurt our eyes or our gear. The sun is a massively powerful source of not only visible light, but also infrared and ultraviolet radiation, and thus we need to respect it. Whatever you do, don't try your own homegrown sun protection ideas, like stacking sunglasses or using colored plastic. There are many sources of information on how to safely observe the sun, so please take this advice seriously. Observing the sun directly. As we described in video number 2 on the size of the sun, we could recommend that you get a solar filter and either look through it or attach it to your digital SLR. If you plan on looking at the sun with your eyes, get a number 14 welder's glass. The disadvantage is that since the sun only takes up about a half a degree of view, only the largest sunspots will be visible. But there's no comparison to just staring at the perfect circle that is the sun. With protection, you can look at it as long as you like, and it's quite beautiful. If you do observe the sun by holding up a number 14 filter to your eyes, you could sketch any sunspot pattern in your logbook. Just draw a circle to represent the sun and draw dots for any sunspots you see. Please be aware that only massive sunspots will be visible in this manner, and these don't happen often. Photographing the sun. If you use a camera, you'll need solar film. Be very careful that you get the film designed for telescopes and binoculars, as there is a completely different product also called solar film, designed to stick to windows to help reflect heat. If you use solar film, you can use various methods such as cutting out a circle of film and taping it to a cardboard frame and mounting it to the front of your camera. Be very careful that the film won't fall off or you could fry your camera sensor, especially when zoomed into the sun. These photos are from an excellent article at ozscopes.com.au. We're including the link in the description. If you use a glass filter, a very inexpensive method uses a reversible lens hood and rubber bands. When mounted backwards, the lens hood provides ears around which you can wrap the rubber bands. Step 2. Optional. Making a solar clinometer. This is a completely optional project and complements our previous video on the path of the sun. But as you'll see, an analysis of sunspot movement in one day will require that we be mindful of the sun's path. To make a simple but accurate clinometer, you'll need a protractor, pencil, scrap of cardboard, thread or dental floss, and a small weight like a clothespin or a binder clip, plus some tape. It's best to get a protractor that has a small hole at the origin or center. This is where the vertex goes if you're actually measuring angles. Start with a small piece of cardboard, 1 3 inches wide is plenty big enough, and punch the pencil through the cardboard so that only the eraser is sticking out to make a small handle. Then tape the straight edge of a protractor to the shaft of the pencil. Be careful that the edge makes contact with the pencil for the full length, with no gaps, but no overlapping either. Thread the dental floss or thread through the hole and tape on the far side. The hole will keep the thread centered. Instead, I used a piece of toothpick and tied it to the floss and then threaded it through. I don't recommend tying the floss to the protractor through the hole because then it won't be centered. Then attach a clip or a small weight to the end of the thread. Your solar clinometer is now complete. To use the clinometer, hold the handle and point the pencil at the sun so you see its shadow on the cardboard. The protractor and thread will hang below the pencil. Then carefully align the clinometer so the pencil is precisely pointed towards the sun so that its shadow disappears. Then as carefully as you can, while keeping the pencil pointed in that position, read the measurement on the protractor between 0 and 90 degrees. Can you tell what the protractor reads in this photo? In my example, the clinometer reads 68, or 68 1/5 to be more precise. If you held the pencil horizontally, the protractor will read 90 degrees, and if you point the pencil vertically, it will read 0 degrees. This means to get the actual angle of elevation of the sun, we need to subtract our reading from 90 degrees. In my example, I found the elevation of the sun to be 22 degrees, or more accurately, 21.8 degrees. If you'd like, you could see what suncalc.org says. Just make sure you enter your location and the exact time of the reading to the minute. I found a very close result when I tried it, but your results may vary. Step 3. Making observations. As with previous videos, we recommend that you record all your results in a logbook, such as a simple composition book. Start your log with the day's date and the official times of sunrise and sunset, along with your location. A compass bearing diagram, which you can print from the internet, is helpful in recording the direction we're facing when making observations. Compass directions include the familiar phrases like north by northwest, and bearing simply applies a compass rose to a 360-degree circle, with north being 0 degrees, counting clockwise. Before you record any observations, you'll want to orient your compass bearing diagram with true north. You can use a local map of your area or some other resource you trust to find true north, and simply place the diagram on the ground beneath your feet or on a table in front of you. Each time you make a sun observation, use your solar clinometer to get the elevation angle of the sun and record your direction using the compass bearing diagram. You can also sketch the location of any visible sunspots in your log. Simply draw a circle and mark the location of any spot with a dot. Repeat this process throughout the day if you can see sunspots. Here is a sample logbook page. Pause the video here to record the details. Step 4. Analysis. We will break our analysis into 3 parts. The first 2 parts are theoretical. We see a circle, but what is the actual shape of the sun? Second, how do we look up to see objects in the sky? The third part is practical. If we were able to see sunspots, how do the features move across the sun in one day? Analysis Part A. Possible shapes of the sun. Here we're going to consider the potential shapes or objects which result in viewing a perfect circle. One aspect of conducting our own backyard experiments is that we make no assumptions, even when they seem obvious. We want to thoroughly examine the possibilities. We all know that the sun looks like a circle, but what is the actual shape of the sun? There are words like disk, spotlight, and sphere tossed around when discussing the sun in the flat earth debate. In this section, we'll analyze what shapes look like a circle. In 2 dimensions, we have a circle and an ellipse. In 3 dimensions, we have some hard-edge shapes with a circle at one end, such as a cone or a cylinder or a disk. Lastly, we have some soft-edged shapes, which might look like a circle, such as spheroids and spheres. What are the restrictions when viewing this variety of shapes? They don't all look like circles all the time. For example, a cone looks like a circle when viewed from the flat base, but looks like a triangle when viewed from the side. This table summarizes the restrictions on viewing these shapes. You'll notice that in most cases, the shape needs to be viewed on axis to appear to be a circle. Can we be more precise with this? Before we go further, let's test your perception. We'll start with an image of a circle, and then I'll present you with 4 more images labeled 1, 2, 5, and 10. Let's see if you can tell which are circles and which are not circles. 1, 2, 5, 10. It was a trick question, as none of them were circles. Here they are again. 1, 2, 5, 10. The numbers referred to what percent away from being a circle they were. For example, in this shape, marked 5, the width was 5% less than the height. Human perception can be quite sensitive at times, and many people can tell when a circle is out of whack by only 5% or so, but some people can tell much sooner, like at 1 or 2%. The bottom line is that just about everyone will see a shape with 10% deviation from a circle as an oval, not a circle. So what does this mean mathematically? Let's take an observer facing a circle. If we add a second observer off to the side, what do they both see? Only the first sees a circle. The second one sees an oval. The question is, how far away from straight on does a circle start to look like an oval? Let's consider the same situation, this time with a top view. The yellow line represents the top edge of a circle, and the capital R represents the actual radius. Our viewer off to the side is deflected by a small angle theta. The viewer on the side sees the same height of the shape, but it appears narrower, shown by the lowercase r. Here, we've magnified the triangle, making it clearer the relationship between the actual radius, capital R, and the observed radius, lowercase r, and the triangle they make with the angle of deflection, theta. The cosine of the angle of deflection theta is the ratio of the apparent radius to the actual radius. The inverse cosine lets us start with the ratio to find theta. Remember our 4 test ovals labeled 1, 2, 5, and 10? These can be rewritten in terms of ratio of width to height, 99, 98, 95, and 90%. Let's plug in these values from our test ovals to find the angles of deviation. For example, an observer would need to be 8.1 degrees off axis to see the circle as a 99% oval. Here's a scale drawing showing these exact angles from 8.1 degrees to 25.8 degrees. For a better visual, let's add the images of ovals, with the last one being obviously not a circle. This means that if we observe a circle or a circular shape from just 25 degrees off center, it will obviously appear to be an oval. So how does this relate to the actual shape of the sun? Again, the sun can be a flat disk or a spotlight such as a cylinder or cone, or a spheroid or a sphere, depending on what angle you look at it. If the sun is small and close, such as in the flat earth model, you could figure out what shape it needs to be to appear to be a circle from all angles. The heliocentric model has a spherical sun 93 million miles away, so the other shapes such as cones and cylinders may just be an academic exercise in geometry, but we wanted to cover all possibilities in this presentation. Analysis Part B, Looking Up. If you have a clear view of the sky, it can be thought of as a sky dome. You have a 360-degree horizon, and from any point on that horizon, it's 90 degrees to the point straight over your head. It's a virtual hemisphere of sky. So how do we look at something in the sky? If it's not directly overhead, we simply face the object and look up. This concept is so simple, most people who look at heavenly objects don't consider it. When we look at Earth-based objects, such as airplanes, hot air balloons, birds, and clouds, we don't give it a second thought. Our up and down are the same as their up and down. So how do we look at the sun or moon? We don't cock our head and look up at an angle. We simply face it and look up. We also therefore expect that its up and down orientation is the same as ours, which might not be the case, especially in the globe Earth model. To illustrate this, consider an observer facing the sun on the globe Earth. For our observer, up is obvious. It's an arrow pointing away from the ground. But up for the sun's path might be very different. We'll analyze this further when considering the behavior of sunspots in the next part. Analysis Part C. Sunspots in the flat Earth versus globe Earth models. If you are unable to see your own sunspots, we're including links to several sunspot videos with images taken throughout a single day. Please note that there are other sunspot videos available online which are taken over a series of days and weeks, which show the progression of sunspots across the sun over many days. Our analysis only concerns how the orientation of the sun may change in one day, so we're including links to the description box for this video. We'll start with the flat Earth model, which has the sun about 3,000 miles in altitude, circling the North Pole, traveling above the equator or tropics. To analyze sunspot motion in one day, we'll examine a few possibilities for the orientation of the sun as it moves through one day of sunshine for North America. One possibility is that the sun maintains a fixed orientation with zero rotation. Notice in this image, the colors of the beach ball don't change orientation as the sun goes through 12 hours of daylight. How will this relate to sunspots visible from North America? If you examine the colors of the beach ball and the side facing North America, you'll see them appear to sweep to the right, as the viewer first sees yellow, then blue, then red. A similar left-to-right sweep will be seen from the southern hemisphere. What if the sun maintains its orientation with respect to the North Pole? In our beach ball illustration, it keeps the yellow panel facing north, but an observer in North America will see the yellow slightly to the left at sunrise, then slightly to the right at sunset. This means the sunspots should sweep slowly left to right across the face of the sun. What if the sun has some other pattern of orientation? Regardless of the pattern, the movement of sunspots should reveal a three-dimensional sphere moving above a flat Earth, as viewed from below, because different viewers see different faces of the sun. In the globe Earth or heliocentric model, the sun is at the center, and thus essentially doesn't move in relation to the Earth. It is the rotation of the Earth on its axis which gives us day and night, and produces the apparent movement of the sun in the sky. We discussed the path of the sun in the sky in detail in video number 4. What is important here is that in one day's worth of sun, it keeps the same face pointed towards the Earth. As the sun apparently moves on this path across the sky, it will keep its same orientation with respect to its path, even though our angle of view changes, as we'll see in the next few slides. Remember how we discussed the natural way to look at a sky object? We face it first and look up, without cocking our head at an angle. This precisely relates to how we view the sun throughout the day. We'll examine how this looks from the northern hemisphere, the tropics, the southern hemisphere, and the Arctic and Antarctic regions. In the northern hemisphere, when we view a sunrise, we just look at it without regards to the sun's path. But we see that the sun maintains its orientation on its path, not in relation to our horizon line, where we happen to be standing on the globe Earth. Thus, the face, or disk, of the sun will appear to rotate clockwise about 90 degrees in one day's worth of sun. What about in the tropics, such as at the equator on the equinox? The sun will rise almost straight up from the horizon and will pass directly overhead. If we consider the sun's orientation on its path, it will appear to maintain the same orientation for the first half of the day, but switch 180 degrees and maintain that new orientation for the second half of the day. What about at noon? It's hard to say, since the sun is nearly directly overhead. This means you can face in any compass direction or bearing and look straight up. There's really no preferable direction to face. The southern hemisphere's sun path is similar to the north's. The sun still rises in the east and sets in the west, but the sun will spend most of its time in the northern part of the sky. This time, the face or disk of the sun will appear to rotate counterclockwise about 90 degrees from sunrise to sunset. Lastly, we have the Arctic or Antarctic regions. The sun takes a very shallow path across the sky, thus the disk shouldn't rotate much. Here's a slightly different explanation for the same phenomenon. Let's take an observer in the United Kingdom looking due east away from us. The sun is 93 million miles away through our computer monitor. We are peering over the shoulder of our observer looking at the sun. Our observer sees the sun tilted to the left. Fast forward 12 hours later, and our UK observer is now facing west, away from us, watching the setting sun. From this new perspective, the sun appears to be tilted to the right. Let's summarize what we've learned about the sun's orientation in the globe Earth model. Since it is so far away from Earth, it shows the same face towards all observers on Earth. The only variable is the angle at which the Earth observer is looking. This results in different images of the sun rotated in a disk-like circle from each other. In the middle latitudes of the northern and southern hemispheres, for example 45 degrees north or south latitude, the sun's disk should appear to rotate 90 degrees. In the Arctic, the sun's disk should rotate very little, while in the tropics, the sun's disk should maintain the same orientation for the first half of the day, then flip 180 degrees and maintain that for the second half of the day. Let's recap what we've learned in this video about the shape and features of the sun. The shape of the sun can be anything, a cone, a cylinder, an ellipsoid, even a disk, as long as it presents as a circle for all viewers at all times. Even a circle won't appear circular, just 25 degrees off axis. With regards to sunspots in the flat Earth model, sunspots should sweep across a 3D rotating sun as it moves over and above the flat plane of the Earth. Different viewers and even different times of day will reveal different faces of the sun throughout a single day. In the globe Earth or heliocentric model, sunspots won't move in one day, but they appear to rotate around the face or disk of the sun, depending on time of day and latitude. So how do your results stack up? Were you able to observe sunspots throughout the day? If not, be sure to watch those 3 videos with sunspot footage. Do you want to share your results? YouTube user Cara Diann has created message boards for folks to share their results of these flat Earth experiments. This is not a forum to debate flat Earth versus globe Earth, but rather one for folks to share their results when they do the experiments. We've included a link in the description box of this video. Come join us. Please remember that the results from this experiment won't necessarily prove the flat Earth versus the globe Earth. They might simply support one model over the other. To be more certain, more data gathering is needed as our series continues. Our next video will kick off our moon series with Size of the Moon. You'll just need a good quality digital SLR and a tripod. When commenting on this or any other video, please keep an open mind and remember to be kind to each other. Practice what Stephen Covey recommends. Seek first to understand, then to be understood. Thank you.